Okay, I think we can start. So, just briefly say where we are. We are discussing that introduced the Nullstellensatz. Theorem of zeros. So, we have the weak Nullstellensatz said that if you have an ideal in polynomial rings and variables, which is not equal to the whole polynomial ring, then it follows that its zero set is empty. It's non-empty. And so we were going to prove that later. And as a consequence of this, we proved the strong form of the Nullstellensatz, which said that again, if I in k x1 to xn is an ideal, then it follows that the ideal of the zero set of this ideal, or the set of all functions which vanish on the zero set of the ideal, is equal to the radical of the ideal, which is would be the set of all polynomials, such that some power of them, such that the power of them lies in the A's. And this we in particular would get a 1-1 correspondence between radical ideals and project and finite right sets. Then we had started to introduce projective space, and we wanted to talk about projective varieties. So I will repeat more about the projective space. So this was just Pn, the n-dimensional projective space is just k to the n plus 1 without the origin divided by some equivalence relation, where we have that in n plus 1 tuple a0 to an, n plus 1 vector in n plus 1, which is not 0, is equivalent to lambda a0 until lambda an for all lambda in non-zero element in K. So we have, we identify two vectors here if and only they are multiples of each other, and the space of all these equivalence classes is projective space. We denote a0 to the n, the point, the equivalence class of a0 to an. We had seen that we can cover this by some subsets which look like a fine n space, namely if you put ui equal to the set of all points in projective space a0 to n, such that the ith coordinate is non-zero, then we had seen that via some phi, this is actually bijective to n. So maybe phi I, so well, maybe I don't write in this case what the, and the inverse map I call ui. I just for simplicity write it in the case n equals 0. So u0, small u0 of a point a1 to an in an is defined to be just we add the 1 at the beginning and make it into point of projective space. and you can imagine how it works for the others. And we see, as I said, both methods are bijective, and I use often this U0 to identify AN with a subset U0 of Pn. AN with U0 in Pn. And so if we make this identification, so we identify the point A1 to AN with this one, we would get that Pn is equal to AN union what is called the hyperplane at infinity, where this is equal to the set of all, obviously the set of all A0 to AN in Pn, such that the zeroth coordinate is 0. So I could have just written like this. Okay, so that's where we were, and now we are interested in, we want to do algebraic geometry, so we want to look at algebraic sets, so 0 sets of polynomials. So we want to define algebraic sets as 0 sets of polynomials in Pn. So this will be projective algebraic sets. So obviously, as we, on this space we have n plus 1 coordinates, so we need polynomials. We need to use polynomials in n plus 1 variables, and so. Okay, we could just say we take the 0 set of these polynomials, but you see there is a problem. So if I take a polynomial g in k x0 to xn does not define a function. On Pn. No, it's not like, obviously, how would you want to define this? You put the coordinates of the point P in Pn into this polynomial, and then you evaluate it at this. But now the points in projective space are equivalence classes. If you take another equivalence class, you get another result. So they are not functions. So in fact, for instance, if I look at the following, if I take, for instance, g equal to, if I got it right, x0 times x1 minus x2, why not? Then if I take f of 1, not g of 1, 1, 1, what is that? This is 1 times 1 minus 1, this is 0. And g of, say, 0, 1, 1, this is 0, minus 1, this is minus 1. So you can see that for the same point, what did I want to say? Forget it. Now I'm not quite sure why I was confused. Okay, so let's look at this again. So look at this thing. So if we take g, I can, what I said had no relevance, but anyway, if I take g of 1, 1, 1, this we saw was 0. And if I take g of 2, 2, 2, which is the same point in projective space, this is 4 minus 2, this is 2. And so, not only does the value depend on the representative, but also the question whether we get 0 or not depends on the representative. So we certainly cannot, say, we cannot talk about the zeros of this polynomial in this sense. But if we look a bit more careful, if the polynomial is homogeneous, of a certain degree. It still doesn't define a function, but the question whether it's 0 at a point in Pn makes sense. Let's see why. So, however, if G in Kx0 to Xn is homogeneous, then whether G of A0 to the n is equal to 0 depends on the point in projective space A0. Why is that? So we can just look at it. Namely, can call it math. So if I say that G in K x0 to xn is homogeneous of PBD, then if we take G of lambda A0 until lambda AN, I claim this will be equal to lambda to the d times G of A0 to AN. Why is that? That it's homogeneous means that it's a linear combination of monomials, which each monomial is a product of d, of the variables, d of the xi. So if you evaluate it, for each monomial you get the product of d of the AIs, and so far if I multiply each AI by lambda, we multiply the whole thing by lambda to the d. Okay, so this is, and so in particular we see that if this thing is 0 for one representative, it is 0 for all representatives. Whether so if G is 0 for one representative, it is 0 for all. So of a point P at the end. Okay. So so we make this the reason for our definition. So we consider, at least for the moment, but essentially always only 0 sets of homogeneous polynomials, and then a projective algebraic set will be 0 set of a set of homogeneous polynomials. Definition. So let G in K x0 to xn be homogeneous of degree d. So a point P, which with coordinates A0 to n and n is called a 0 of G, and we just write G of P is equal to 0. Well, if G of A0 to n is equal to 0. For 1 and equivalently all representatives of P. Okay, so this means that. So I just write G of P equal to 0 to mean that if I write down any, put in the homogeneous coordinates into the polynomial, then I get 0. It doesn't make sense to say that g of p is equal to 5, no? Because that would depend on the representative. But that g of p is equal to 0 makes sense. And then we do the usual thing. So let S in K x0 to xn be a set of homogeneous polynomials. Then the zero set of S is S, which is equal to the set of all points P in Pn such that f of P is equal to 0 for all f in S. So the common zero focus of all these homogeneous polynomials. So if I want to remember that I'm a projective space, I say the projective zero set. Most of the time, we know where we are in the final projective space, and then we don't mention it. Okay. So a subset of Pn, so this is Pn, of the form V of S is called a projective algebraic set. Again, I will write Z of, as I also read before, F1 to Fr instead of Z of the set F1 to Fr. And so if F is homogeneous of degree D, just introduce all the words that we want to use in the future. If f in kx0 to xn is homogeneous of degree D, we say we would call the zero set of f a hypersurface. Hypersurface. And okay. So it could sometimes happen that we at the same time consider subsets of affine space and projective space. And so then we might want to, so here I've used the same notation as I did for affine algebraic sets. But if we need to distinguish, we put a P for the projective and then A for affine. So if we need to distinguish, write Cp of S for the projective zero set and Za of S for the affine zero set. Okay, so this lies in projective space, this in affine space. Okay. So these were just the words. So now, let's again look at the usual examples. Somehow you can imagine, as things are very similar, that things are extremely similar to the affine case, and many of the results we proved for affine algebraic sets work in the same way for projective algebraic sets with the same proofs, and so we will also not repeat the proofs. But let me first state things and also say what is slightly different. So we have, for instance, as usual, we have that example. So the empty set is the zero set of, say, when we are just 1, and Qm is equal to the zero set of the empty set of polynomials. And so these are projective algebraic sets. And so if f is homogeneous of degree 1, we call the zero set of f a hyperplane. And we already used this word already before. So, for instance, H infinity, the hyperplane of infinity is the zero set of the polynomial x0. So this is the hyperplane at infinity. More. Yeah. So I had claimed before that in, for instance, P2, any two lines intersect. Maybe I will not say that, but we can at least see some lines which don't intersect, which will intersect in P2. So if I take the lines, 1, 2, so the lines, so say zero set of x1 in P2 and zero set of x1 minus x2 x0 in P2. If I restrict them to A1, so A1 would mean I put x0 equal to 1. No, it's the locus where the zeroth coordinate is 1. So restrict. So the parallel lines z of x1, but now in A2, and z of x1 minus 1 in A2. So these are parallel and they don't intersect. But in P2 they do intersect. Namely, you can see the condition is here that the first coordinate is 0 and the difference of the first and the zeroth coordinate is 0. So that will be true if both the first and the zeroth coordinate is 0. So in P2 the intersection is the point 0, 0, 1. So the first and the zeroth coordinate are 0, and then we can normalize this to be 1, which lies on the hyperplane at infinity. Okay, so we can see that these two lines are just two parallel lines like this in A2, but if we kind of add the line at infinity, then somehow, just you could more, it's really project, that's why it was originally called projective geometry. You really think of, how you look at things, you see the horizon, so the line at infinity somehow lies with the horizon, and so they intersect there, and here we have an okay. And actually, one can show that any two, for instance, in P2, any two hypersurfaces will have non-empty intersection. In fact, you have, if once one has a notion of dimension, you have that any two subvarieties whose dimension at least up to n have non-empty intersection in Pn. Whereas in defined space, this is extremely far from being true. Okay, now in the affine case, we were also considering the ideal of an affine algebraic set. In particular, we're also saying that every affine algebraic set was a zero set of an ideal. We want to have the same here. But obviously, we have to now, we have this problem that we need homogeneous polynomials, so we have to somehow make sure we are dealing only with homogeneous polynomials. And for this, we introduce homogeneous ideals. Definition. So if I take any polynomial, f, so in our variable x0, xn, can be written, you can just kind of group together the monomials of the different degrees. So can be written as f equal to f0 plus f1, where fi is homogeneous of degree d. In a unique way, I can write it like this. Just fi is just grouping together all the monomials of degree d. So fi of degree I is called the homogeneous component. Component of f of degree I. And now we call an ideal in this polynomial ring. We call it a homogeneous ideal if whenever it contains a polynomial f, it also contains all its homogeneous polynomials. It's called homogeneous if for every f also all homogeneous components fi are in. Okay, there's a slightly strange definition. It's somehow comforting to see that you can define this in a different way, which might be slightly more natural. Namely, the claim is that it's equivalent to saying that it's generated by homogeneous polynomials. So, whatever. Small, nuclear proposition, small remark. So, an idea. I is homogeneous if and only if I is generated by homogeneous polynomials. That's quite simple. So it's if and only if, so we have to show both directions. So, and both of them are easy. So for instance, so assume I is homogeneous. Let say f alpha is a set of generators. Then each f alpha is some polynomial which lies in I, so each homogeneous component of f lies in I. So thus we have that if I take all the homogeneous components over all possible alpha and I, this is a set of homogeneous generators.
Shouldn't I itself depend on alpha because the number of homogeneous component of a polynomial depends on the polynomial itself?
No, I take all homogeneous components. So I runs over some, over all integers and alpha.
Ah, okay.
No, I don't just take one, I take all. So take all, so this is, alpha is in some set, and I is a positive integer. So that's what I meant. Is a set of homogeneous polynomials, homogeneous generators. Because by definition of homogeneous ideal, these lie in I, and certainly I can write F. I can write F alpha as a sum of its homogeneous components. So therefore, these Fi alpha generate the ideal, because you have generators F alpha in the thing generated by that. So the other direction is not more difficult. So, so we assume I be generated by homogeneous polynomials G alpha. So that means we can write every say F in I can be written F equal sum, say AI, G alpha I, to some finite sum like this, where the AI are some polynomials. That's what it means to be generated by this. Now, as these G alpha I are homogeneous, so say, let di be the degree of G alpha I, so the G alpha I are homogeneous of degree di, then the part of degree, say any degree d of f is fd equal to the sum over the same I, G alpha I, times, so we want the degree to be d. The degree of this is di, so I have to take the part of this of degree d minus di. And so we see it lies in the the ideal is generated. So that means this thing also lies in the ideal generated by these elements, so it also lies in I. Okay, so with every element, every homogeneous component lies. Okay, so this is a simple fact. And now, using this, we can say what we mean by the idea of a projective algebraic set, or what it means to have the zero set of an ideal. So, definition. For I in K 0 to x n an ideal, the zero set of I so this is not an ideal. I take a homogeneous ideal. The zero set of I is z of I, which is the set of all the points P in N, such that f of P is equal to 0 for all homogeneous f. Okay. Only take the zero set of the homogeneous elements, not of all the elements. And in the same way, for x in Pn subset, the homogeneous ideal, usually one says ideal, but if one wants to stress the difference, the homogeneous ideal of x is, so it's usually noted, again just Ix. This is, well, on the first thing, so it's somehow the set of all f in k x1, x0 to xn, which are homogeneous, such that f of p is equal to 0 for all p in x. Now, if I take this set, this is not an ideal, but I take the ideal generated by it. And this is a homogeneous ideal, because obviously by definition it's generated by homogeneous polynomials. So sometimes we again want to consider both something as lying both maybe in a affine space and projective space. So we also want to might sometimes want to distinguish between the homogeneous ideal and the ideal in without this. So if we need to distinguish, right, IH of x for the homogeneous ideal. Okay, so have really not done anything at all, but just now introduced these words. I should maybe mention, because we will not use that much, but we will use it later today, that we were not really forced to restrict our attention to homogeneous polynomials, homogeneous ideals. One can also do without that, but it leads to something being slightly, it's all written there, it leads to a slightly, say, unintuitive situation. And so therefore one usually restricts to the homogeneous case, but let me just say, so remark, if f is just any polynomial, not necessarily homogeneous. We could still say we can define, and P is a point in Pn, we can still define that f of P is equal to 0 if and only if f of A1, A0, or An is equal to 0 for all representatives. A0 to An of P, if I just put any such. Now, that makes some sense, but, and we will actually see that this is reasonable. But note what it means, so you can see as exercise, with this definition, f of P is equal to 0 if and only if fi of P is equal to 0 for all I. So kind of, if I put one equation, so if I take the 0 set of one polynomial which is not homogeneous with this definition, it is the same as the common 0 set of all its homogeneous components. So we have reduced to this. And it's a bit unintuitive because writing down one equation gives you a large number of conditions. But it has some, so at any rate, using this, and we are going to use this later, so if now I in K x0 to xn is a homogeneous ideal, then with this definition, we get, you can check, it's easy to check. First, that the 0 set of this ideal, I mean still a homogeneous ideal, can also be just defined as the set of all P in Pn such that f of P is equal to 0 for all f in I. So if I define what it means to be 0 in this more complicated way, then we get the standard definition. And in the same way, we can also reformulate what the ideal is, namely the ideal of x doesn't have to be the ideal generated by something, but the ideal of x will just be the set of all polynomials f in K x0 to xn such that f of P is equal to 0 for all P. So if we are willing to take this more complicated definition, then we can just write like this, the usual definition as in it. But it's much more convenient to work with the homogeneous polynomials, where you don't have all these hidden conditions, and do everything in terms of that. So now I want to just state some of the obvious properties which have precisely the same proofs as in the affine case. So with the same proof, as in the affine case, we have the following. So we call this proposition. There are simple cases, things, for instance, so if x is contained in y in Pn, then it follows that the ideal of x contains y. No, this is the same thing. No? Take a smaller set, then the functions which vanish on it are more. And so if y into n is a projective algebraic set, then if I take the zero set of the idea of y, then this is y. And okay. And we also have this thing that if j in k x0 to xn is an ideal, the homogeneous ideal, then if I take the ideal of the zero set of j, then this will contain j. No, and there's again, the same statement as before. All the homogeneous elements in J obviously vanish on the zero set of all the homogeneous elements in J. That's what this says. It's the topology. So the same way, if S is contained in T, so x0 to xn, and then it follows that the zero set of S contains the zero set of T. Where I assume here maybe these are homogeneous polynomials. So again, if S in kx0 to xn is a set of homogeneous polynomials, then it follows that the zero set of S is the same as the zero set of the ideal generated by S. No, and we leave the proof, it works precisely the same way. And notice, maybe I can mention this here, so we have that, this is again a polynomial ring, we have shown that such polynomial rings are Noetherian, so this is a Noetherian ring, so every such ideal is finitely generated. So this says, so it means therefore that thus every projective algebraic set is a zero set of a homogeneous ideal. And then, as I said, as this ring kx0 to xn is Noetherian, such a homogeneous ideal is always finitely generated, so it means also every projective algebraic set is the zero set of finitely many polynomials, of finitely many homogeneous polynomials. Anyway, okay, so this is quite. Let me see what else we want to know. So we obviously want to introduce the Zariski topology. So we observe that in the same way as what number 6? If I take if you have a family, so or family, so it's alpha is index set of homogeneous polynomials, of sets of homogeneous polynomials. we obviously have the zero set of the union over alpha of these as alpha is the same as the intersection over alpha with zero as alpha. And this, in the same way as in the defined cases, the tautology, because we just say that all the functions in the union here should vanish there, and obviously that's the same as taking the intersection over those, and in the same way for the other statement. So, so if I have, again, S and T sets of homogeneous polynomials, so subset K plus N. So again, sets of homogeneous polynomials. And then it follows that the zero set of S times T, which just means the set of all products, one element in S, one element in T, is equal to the zero set of S. Union zero set of T. All these things you proved in the defined case, and the proof is the same. So in particular, you see that these statements say that arbitrary intersections and finite unions of projective algebraic sets are projective algebraic sets. So with this, we find therefore that the projective algebraic sets define the closed sets of a topology of Pn. So definition is a heuristic topology on Pn is the topology whose closed sets are the projective algebraic sets. Okay, so we have this topology, and again, any subset of Pn, we give the induced topology. In particular, this will be true if X itself is a projective algebraic set, is given the induced topology. Induced or subspace topology which will be called the heuristic topology on X. So we have in particular that all projective algebraic sets are large topological spaces. We will, an open subset in a projective algebraic set will be called a quasi-projective algebraic set. So this is something we use often in this word, an open subset in a projective algebraic set. Is called quasi-projective algebraic set. If we make our identification that An is a subset of Pn, then it is an example of that. So with our identification, that An is just considered to be equal to this subset U0, which is Pn without the hyperplane infinity, which is the zero set of X0. We see, therefore, that AN is a complement of a closed set, so it is an open subset. We get that AN is quasi-projective. And finally, we can also use what we said about so as a consequence of Hilbert's basis theorem, that we had seen that every fine algebraic set has decomposition into irreducible components, and that is because it is, with the topology, a Noetherian topological space. And so we have the remark that as in the affine case, what we now show, I want to see that Tn is a Noetherian topological space. So what one has to show, that they have any descending chain of closed subsets, then it becomes stationary. So that x1, so Tn means x1, 2, in infinite chain of closed subsets. I'm not even sure, maybe I forgot to write that one. Oh no, I didn't. So I have infinite chain of closed subsets like that. Then if I take the corresponding ideals, also the homogeneous ideals, Ix1 contained Ix2 is a chain of ideals in Ax0 plus n of homogeneous ideals, and so it becomes stationary. So we have from some point I xn is equal to I xn plus 1 and so on. And as we know that x, whatever, xl is equal to the zero set of the ideal of xl, no, that I think I just wrote on the blackboard. So by is it follows that xn is equal to xn plus 1, and so on. So the chain of closed subsets becomes stationary, which means that it's a Noetherian topological space. And then we had this theorem that every Noetherian topological space has a unique decomposition into irreducible components. So, but maybe let me first say one more thing. We know, so we have seen that every subspace, every subset with the induced topology of a Noetherian topological space is Noetherian. So thus, every quasi-projective algebraic set is Noetherian as a topological space, and by our theorem it follows that every, we call it x has a unique decomposition, or I just say has a decomposition into irreducible components. mean by that is clear. So X can, in a unique way, be written as a finite union of irreducible quasi-projective algebraic sets and this decomposition is unique if I put the condition that none of them is contained in another. Okay, so as you see, so this was very fast, but we have done everything again that we did in the fine case. The arguments are the same. Here, this can also serve for you as a review of what we did when we did this. But you can see it's all quite straightforward. And so now we have this decomposition into irreducible components. So maybe I write this explicitly. So corollary every quasi-projective algebraic set has a decomposition. Equal to X. X equal to 1 XR into irreducible components. Okay, so that's this. Now, the last thing that we proved for affine algebraic sets was the Nullstellensatz. And so, we are kind of have given ourselves a task of doing everything again, and so now we state and prove a projective version of the Nullstellensatz. First, let's find out what this even would mean. So we want to show a projective version of it, and we will, not kind of try to reinvent the wheel, but we will want to, to prove this version as a consequence of the Nullstellensatz we already proved in the affine case. And so, therefore, we will have to find a way how to relate a projective algebraic set in projective space to an affine algebraic set in affine space, so that somehow the statements of the Nullstellensatz in both cases become more or less equivalent. And this we do by looking at cones. So basically, if we take a projective algebraic set, it's given by the zero set of some homogeneous ideal. If in projective n space, if we take the zero set of the same ideal in a affine space one dimension bigger, this will turn out to be a cone. And the usual Nullstellensatz for these cones will be equivalent to this projective Nullstellensatz for the projective algebraic set. So let me try to make sense of this. So I want to show projective version we should say I proved this because I will need it sometime in the future when we want to prove that projective varieties fulfill a certain compactness property. So somehow that if you have a map from a projective variety to some other, say projective variety, which means irreducible projective algebraic set, and maybe we should have said that. To another variety, which is in the context of algebraic geometry, this is what we would call a morphism, then the image will always be closed. So that's like a continuous map from a compact set. So in order to prove this, we will need this much in the future. So I want to show this projected version, but I should maybe, before, again, because I just remembered it, so this is the definition. So an irreducible projective algebraic set is called projective variety. And an irreducible quasi-projective algebraic set is not surprisingly called quasi-projective variety. We just say variety because we do not consider more general varieties, although there are more general notions. So now we want to show this projective version of the Nullstellensatz. And we want to do this by reducing to the affine case using cones. Okay, so let me state this. So definition. So a non-empty subset X in, I will always give it in n plus 1, is called a cone. Well, if it looks like a cone, which means that for every point it also contains the line of that, through that point, through the origin. If so, you can either say it like this for all lambda in k, and all p equal to a0 an. In X, we also have that lambda times the point, so lambda a0 times lambda a. Is an element in F. So the picture is that, so here we have the origin, here we have our point P, and then if X contains the point P, it contains the whole line. So it somehow will look, has to hit the origin, so it will somehow look like this. So it has a, so this is the origin. Well, for every point it contains the line through the origin. So it somehow looks like a cone. Normally, when you talk about cone in normal life, you only take half of it, but anyway, let's take here. And so, what if you have a projective algebraic set? You can associate to it the cone in a fine set, in a fine space of one dimension more. X and Pn, the projective algebraic set. So the affine cone over X is maybe I write Cx. So this is just the set of all, you have, so you take all the elements in X, you take all representatives of them, now this is not precisely a cone because these are always, all the coordinates have to be non-zero. To make it into a cone, we add 0. No? According to, if you have a projective algebraic set, then this just means the representatives of this thing are just all the multiples of a0 to n, so we get the whole line except for the origin, and that we put back. So this is this cone. And this is clearly a cone. And so in an plus 1, where now we have somehow taken our coordinates x0 to xn. So and we can, now obviously these two things are very similar. So basically the claim is now that the cone of X is a zero set of the same ideal as X, only as the ideal of X, but now the zero set is taken in n plus 1 instead of Pn. So let me state this precisely. Let X different from the empty set be projective algebraic set. Then the idea, so one thing one could say like this, the idea of the cone of X, so this is now the ideal in the fine space, is just equal to the homogeneous ideal of X. And the second statement is the other way around. So if the empty set, if X is not the empty set, and it's the zero set in projective space of some homogeneous ideal, then, so this is in Pn, then if I take the cone of X, this is the zero set in a fine space of the same ideal in an plus 1. Okay, so basically we just, and in some sense it's kind of, if you just look at it, it's kind of, so this is more or less by definition. It follows also, the easiest way to prove it is by using this remark I made that you can describe the ideal of X as the ideal of all polynomials which vanish at all points in X, where the polynomial doesn't have to be homogeneous with this different definition of vanishing, and in the same sense that the zero set is the zero set of all polynomials in I. Anyway, I leave the first one maybe to you as an exercise, and give you the second. So from the remark above, so that so the remark that I said about that the zero set of an ideal is just the zero set of all polynomials, if we define what the zero set is by saying it should be zero for all representatives, because that's precisely what's written here. And I will just prove two. As I is homogeneous, and we know, so I is a homogeneous ideal, and its zero set is not the empty set, which doesn't contain constants. We see that ZA of I is a cone. Because you see, by definition, if you have a homogeneous polynomial and the point is a zero of a homogeneous polynomial, then all the multiples of the point are a zero. So the zero set of a homogeneous ideal will always be a cone. So by definition, we have that X was the zero set of this thing. This is the set of all B0 to n, such that lambda E0 to lambda n is in the defined zero set of I. This was this remark I made for all lambda. Okay, so which precisely so this, but this in other words just says that so as I say that C of X, which is precisely so C of X is precisely also the set of lambda this where A lies, where A0 to n lies in X, so the C of X is therefore equal to the defined zero set of I. Okay, maybe I said it a bit fast, but okay, you can. So this is, anyway, this is rather obvious that you see that somehow the whole point of these cones is that you take the zero set of the same ideal once in a affine space and projective space. And so this allows you to transfer to properties from affine to projective space. Because if you can describe the property in terms of the ideal, then you have the same ideal, so the properties will correspond. And so let's then do the projective Nullstellensatz, which is not such a big story. This so we take the homogeneous ideal. difference. You know, we have kind of the weak Nullstellensatz and the strong Nullstellensatz. The weak Nullstellensatz would be if you take the zero set of this ideal, this is empty, where normally if we are looking in the fine case, the zero set of an ideal is empty if and only if the ideal is the whole polynomial ring. We don't quite get that. We get the weaker statement. This is if and only if I contains all homogeneous polynomials of degree n for some n. So I does not have to contain all polynomials, but at least if I start from a certain minimal degree, from then on they will contain all of them. And the second statement is that, however, once I get rid of this tiny issue with the empty set, it's the same as in the fine case. So if the projective zero set of I is not empty, then the homogeneous ideal of the projective zero set of I is the radical phi. So we get the same formulation as in the fine case, only that we take the projective ideal in the projective zero set projective space, except for this tiny difference when we're looking at the empty set. And there's in what I've wiped out, one can see the reason of it, but anyway, we'll now prove. So we take x to be, so we either this zero set of this ideal, and so if now x is the empty set, so we always have to relate to the cone of this thing. So what's the cone of the empty set? Then it follows that the cone of x, so this is if and only if the cone of x is equal to 0, because you have added the 0. And somehow this now will be responsible for this difference. So before, we had seen that this equivalence which we had before, that the cone over x is the affine zero set of the same ideal, only holds if x is not the empty set. But what we can see is that this is, if we look at this ideal of the cone, so anyway, so the affine zero set of the ideal must now be contained, so either the affine zero set of the ideal is 0, or it could also have been that the ideal zero of the zero set is the empty set. No? If I take the corresponding projective thing, so I only know that either it doesn't contain a line, but so here we get 0, but the 0 could have come from the fact that we have added the 0, or the 0 was already there. So we can only deduce that the affine zero set of I is empty, or the affine zero set of I is 0. No, because Cx is equal to the affine zero set of I union 0. Okay, once we have this, we can now apply the Nullstellensatz in the fine space to this.
But we have proved that C of x is ZAI, right?
No, this was under the assumption that x is not empty.
Oh.
And if you look at what we are doing, what is actually true is that it's this. Because we are using that as a cone. So by the Nullstellensatz, so we could say this, in a more fancy way, we could say that the A of I is contained in this set. Or if we find that more. By the Nullstellensatz, we find that the radical of our ideal I, which is the ideal of the C x contains the ideal of 0. The ideal of 0 is the ideal generated by x0 to xn. So, thus, for all I from 0 to n, there exists a number ji with xi, so the ji is an element in I. The radical of I contains this, so it means that I itself contains some, there exists a power of it so that it contains that, because this, the radical just means of a set I is just the set of all polynomials such that the power of them lies in I, so that's precisely this. Okay. And so put n equal to J0 plus Jn, then our ideal will contain all monomials of degree n, and therefore then I contains all homogeneous polynomials of degree n. And you can also see why, how this comes to pass, this exception. So in projective space, the class of the origin is not there. So if you take polynomials which only vanish at the origin, they don't play a role. And so therefore we have this. And so anyway, we have this. And now the second statement is simpler. So we take x equal to the projective zero set of our homogeneous ideal I. Well, we have this already. And so as x was assumed to be non-empty, we have that the homogeneous ideal of x is equal to the idea of the cone of x. No? That's what it is, which is the idea of the affine zero set of x. And now we are in a affine of I. So we have an idea in kx0 to xn, look at it's a fine zero set in an, then the ideal of that is the radical of I. By the Wunschdense. Okay. So this was this. I even went over time. I didn't. So I'm worried what I should say next, but then. Okay, so then maybe that's a good moment to stop.